All right, so I'm working off of the investigation number 16 in the book on page 255, and I've just kind of copied down the graph that they have in your textbook so that we can start answering these questions. So this example is going to basically solidify connections between F prime, and F double prime. So eventually what we're getting at is we're going to start reverse engineering these functions if we know something about the derivative function or if we know something about the second derivative function. So we're going to make connections between all three of these and understand the relationship so we can get pretty accurate graphs of the original function. All right, so if you're looking in the textbook, we're looking at copy the graph, and we already did that. So number 2 says, on the same set of axes, mark points which show the value of f prime for points A, B, C, and D, and label them A prime, B prime, C prime, D prime. So if I'm looking at A, B, C, D, and I want to know the slope or the gradient at those points, well, we've already been working with the idea that we know it's a horizontal slope or a horizontal gradient. And anything with a horizontal slope, well, the value of a slope when it's horizontal is just 0. So if I wanted to find f prime at that point, so f prime at the point A, if A were the x value, then I know that the value would be 0. F prime would be equal to 0. The slope is 0. So when I start graphing my derivative function, we kind of looked at this in class the other day, is that would be a value of 0 right here. So anything in blue is going to be my derivative function. Same thing for B. So this is A prime. This is B prime. C prime is also a slope of 0. And then D prime is also a slope of 0. So all of those 0 slopes wind up being zeros on the y-axis when I graph f prime of x. All right, number 3, what are the intervals in which f is increasing and decreasing? What does this tell you about the sign of f prime in each of these intervals? So I can see decreases happening here, increases here, decrease, increase, decrease. So if I wanted to report my intervals of decrease, I might say something every value from negative infinity to a. So I do like negative infinity up to a, and then from B to C. So anything with those, negative slopes, and then from D to positive infinity. Okay, so then if I wanted to look for intervals of increase where the function has positive slope, how about from A to B? Oops. Union with C to D. Okay, now let's go back to this idea of f prime again. What does it mean for f prime, or what does it mean about f prime if your function is increasing? So do you remember that on a sign chart, if I wanted to build a sign chart here, I might have like A, B, C, D, so these are those values. Well, if something is decreasing, it has negative slope, so that means it's negative here. If it's increasing, I have positive slope. So my sign chart would look like this. That's what these slopes are telling me about f prime, is I have these negative values for f prime, literally negative values. So for number 4, it says, use our answer to number 3 to help you complete a sketch of a graph for f. Here's what they mean. If I want to graph f prime as a function itself, then these are actual function values for f prime. So it's 0 here, but on the left of that, where the slopes are negative, that means f prime's function is negative. So maybe something like that. And I'm not being super specific, but take a look that as I continue up, those slopes get really steep in a negative way. So I know that the slope values are getting bigger and bigger down here along the y-axis. All right, how about from A to B, they're increasing, they're positive. So they're positive up here, and then they go to 0 again at B. For C, I know that, or between B and C, the values are negative. So they're going to be like negative and then back to 0. Between C and D, again, they're positive. So I'm literally graphing f of x up here on the positive side of the x-axis. And then they go back to being negative slopes again that are getting bigger. Okay, so there's kind of a sketch of f prime. And notice how when the slopes are negative, f prime is negative down here. When the slopes are positive, when the gradient is positive, that means f prime is actually positive, so it's above the x-axis. Okay, number 5, what key points of f do the max and min points of f prime correspond to? Label these. Now, we've already talked about this. I know, and I'm going to switch colors here, that when I have a slope of slopes, so when I'm looking at the rate of change in my slopes, basically, sure, they're all positive, but they're positive and they're kind of increasing, and then at some point they start kind of decreasing. They're not positive as quickly, like they're not, so here everything's moving in like an increasing sort of way, and then the slopes start decreasing, getting smaller. So these are inflection points. Whenever the slope of your slopes is 0, that corresponds to an inflection point. That happens here. So the slope of f prime is 0. So that corresponds to an inflection point there. Here, 0 again. It's kind of an inflection point almost on the graph, just at that spot. So I have 3 inflection points. And that comes from my double prime function. And again, just to really like hit this home, the inflection points are where I go from concave up to being concave down. So it's those switches. Okay, number 6 says, what are the intervals for which f is concave up and concave down? What does this tell you about the values for f prime? So remember that if I'm concave up, and I can't be super specific about the intervals there because they're not really giving me very specific values to use, but essentially if it's concave up, that means that f double prime is positive. So positive if it's concave up. And then anywhere that the original function is concave down, that tells me that f prime, or double prime, is negative, and it's down. So we can kind of keep those running ideas in our head. Double primes tell us about concavity. Concave up means that double prime is positive. Concave down means double prime is negative. So 7, on the same axes, mark points which show the value of f prime at points E, F, and G. Label the points E prime, F prime, and G prime. I'm losing track of being able to do this very well. I'm going to try. So the inflection points are like anywhere that your slopes are a max or a min. So just those inflection points that we already pointed out. Okay. And then complete a sketch of f. So notice here that the slope of my slopes, the slope of the blue line, the slope of slopes is positive. So that means my f double prime should be positive up here in the positive areas. Okay, then the slopes become negative. So here to here are negative. So I go negative. And then slopes again become positive. And I'm looking at the blue line, so the slope of my slopes becomes positive, and then they're all negative again. So the green line is my second derivative, and it looks really crazy to put all of these on the same axes, but I very much encourage you to like try these out on your own, and then you'll start kind of understanding and seeing, maybe using highlighters and stuff like that for colors. Okay, So describe how you can sketch the graph of y equals f prime and y equals double prime from the graph y equals f of x. So looking at the points of inflection kind of give you clues on double prime, right? F double prime. Looking at points of inflection. Looking at max and mins. Those things help you to find your first derivative function. And again, it is one of those things that just takes those moments of self-reflection and working through this on your own to really see it. I highly encourage you to just make up your own squiggly functions. So making up your own little, squiggles like this, and then asking yourself, what does the first derivative function look like? Where is it equals 0? Where are things increasing or decreasing? And then looking at your second derivative function and finding points of inflection. So there's kind of an introduction on those relationships between the original, the first derivative, and the second derivative functions.